Preface. If at first an idea does not sound absurd, then there is no hope for it. Albert Einstein. One day, would it be possible to walk through walls? To build starships that can travel faster than the speed of light? To read other people's minds? To become invisible? To move objects with the power of our minds? To transport our bodies instantly through outer space? Since I was a child, I've always been fascinated by these questions. Like many physicists, when I was growing up, I was mesmerized by the possibility of time travel, ray guns, force fields, parallel universes, and the like. Magic, fantasy, science fiction were all a gigantic playground for my imagination. They began my lifelong love affair with the impossible. I remember watching the old Flash Gordon reruns on TV. Every Saturday, I was glued to the TV set, marveling at the adventures of Flash, Dr. Zarkov, and Dale Arden, and their dazzling array of futuristic technology. The rocket ships, invisibility shields, ray guns, and cities in the sky. I never missed a week. The program opened up an entirely new world for me. I was thrilled by the thought of one day rocketing to an alien planet and exploring its strange terrain. Being pulled into the orbit of these fantastic inventions, I knew that my own destiny was somehow wrapped up with the marvels of the science that the show promised. As it turns out, I was not alone. Many highly accomplished scientists originally became interested in science through exposure to science fiction. The great astronomer Edwin Hubble was fascinated by the works of Jules Verne. As a result of reading Verne's work, Hubble abandoned a promising career in law, and disobeying his father's wishes, set off on a career in science. He eventually became the greatest astronomer of the 20th century. Carl Sagan, noted astronomer and best-selling author, found his imagination set afire by reading Edgar Rice Burroughs' John Carter of Mars novels. Like John Carter, he dreamed of one day exploring the sands of Mars. I was just a child the day when Albert Einstein died, but I remember people talking about his life and death in hushed tones. The next day, I saw in the newspapers a picture of his desk, with the unfinished manuscript of his greatest unfinished work. I asked myself, what could be so important that the greatest scientist of our time could not finish it? The article claimed that Einstein had an impossible dream, a problem so difficult that it was not possible for a mortal to finish it. It took me years to find out what that manuscript was about. A grand, unifying theory of everything. His dream, which consumed the last 3 decades of his life, helped me to focus my own imagination. I wanted, in some small way, to be part of the effort to complete Einstein's work, to unify the laws of physics into a single theory. As I grew older, I began to realize that although Flash Gordon was the hero and always got the girl, it was the scientist who actually made the TV series work. Without Dr. Zarkov, there would be no rocket ship, no trips to Mongo, no saving Earth. Heroics aside, without science, there is no science fiction. I came to realize that these tales were simply impossible in terms of the science involved, just flights of the imagination. Growing up meant putting away such fantasy. In real life, I was told, one had to abandon the impossible and embrace the practical. However, I concluded that if I was to continue my fascination with the impossible, the key was through the realm of physics. Without a solid background in advanced physics, I would be forever speculating about futuristic technologies without understanding whether or not they were possible. I realized I needed to immerse myself in advanced mathematics and learn theoretical physics, so that is what I did. In high school, for my science fair project, I assembled an atom smasher in my mom's garage. I went to the Westinghouse Company and gathered 400 pounds of scrap transformer steel. Over Christmas, I wound 22 miles of copper wire on the high school football field. Eventually, I built a 2.3 million electron-volt Betatron particle accelerator, which consumed 6 kilowatts of power, the entire output of my house, and generated a magnetic field of 20,000 times the Earth's magnetic field. The goal was to generate a beam of gamma rays, powerful enough to create antimatter. My science fair project took me to the National Science Fair and eventually fulfilled my dream, winning a scholarship to Harvard, where I could finally pursue my goal of becoming a theoretical physicist and follow in the footsteps of my role model, Albert Einstein. Today, I receive emails from science fiction writers and screenwriters asking me to help them sharpen their own tales by exploring the limits of the laws of physics. The impossible is relative. As a physicist, I have learned that the impossible is often a relative term. Growing up, I remember my teacher one day walking up to the map of the Earth on the wall and pointing out the coastlines of South America and Africa. Wasn't it an odd coincidence, she said, that the two coastlines fit together, almost like a jigsaw puzzle. Some scientists, she said, speculated that perhaps they were once part of the same vast continent. But that was silly. No force could possibly push two gigantic continents apart. Such thinking was impossible, she concluded. Later that year, we studied the dinosaurs. Wasn't it strange, our teacher told us, that the dinosaurs dominated the Earth for millions of years, and then one day, they all vanished. No one knew why they had all died off. Some paleontologists thought that maybe a meteor from space had killed them. But that was impossible, more in the realm of science fiction. Today, we now know that through plate tectonics, the continents do move, and that 65 million years ago, a gigantic meteor measuring 6 miles across most likely did obliterate the dinosaurs and much of life on Earth. In my own short lifetime, I have seen the seemingly impossible become established scientific fact over and over again. So is it impossible to think we might one day be able to teleport ourselves from one place to another, or build a spaceship that will one day take us light years away to the stars? Normally, such feats would be considered impossible by today's physicists. Might they become possible within a few centuries? Or in 10,000 years, when our technology is more advanced? Or in 1,000,000 years? To put it another way, if we were to somehow encounter a civilization 1,000,000 years more advanced than ours, would their everyday technology appear to be magic to us? That, at its heart, is one of the central questions running through this book. Just because something is impossible today, will it remain impossible centuries or millions of years into the future? Given the remarkable advances in science in the past century, especially the creation of the quantum theory and general relativity, it is now possible to give rough estimates of when, if ever, some of these fantastic technologies may be realized. With the coming of even more advanced theories, such as string theory, even concepts bordering on science fiction, such as time travel and parallel universes, are now being re-evaluated by physicists. Think back 150 years to those technological advances that were declared impossible by scientists at the time, and that have now become part of our everyday lives. Jules Verne wrote a novel in 1863, Paris in the 20th Century, which was locked away and forgotten for over a century until it was accidentally discovered by his great-grandson and published for the first time in 1994. In it, Verne predicted what Paris might look like in the year 1960. His novel was filled with technology that was clearly considered impossible in the 19th century, including fax machines, a worldwide communications network, glass skyscrapers, gas-powered automobiles, and high-speed elevated trains. Not surprisingly, Verne could make such stunningly accurate predictions because he was immersed in the world of science, picking the brains of scientists around him. A deep appreciation for the fundamentals of science allowed him to make such startling predictions. Sadly, some of the greatest scientists of the 19th century took the opposite position and declared any number of technologies to be hopelessly impossible. Lord Kelvin, perhaps the most prominent physicist of the Victorian era, he is buried next to Isaac Newton in Westminster Abbey, declared that heavier-than-air devices such as the airplane were impossible. He thought X-rays were a hoax, and that radio had no future. Lord Rutherford, who discovered the nucleus of the atom, dismissed the possibility of building an atomic bomb, comparing it to moonshine. Chemists of the 19th century declared the search for the philosopher's stone, a fabled substance that can turn lead into gold, a scientific dead end. 19th century chemistry was based on the fundamental immutability of the elements, like lead. Yet with today's atom smashers, we can, in principle, turn lead atoms into gold. Think how fantastic today's televisions, computers, and internet would have seemed at the turn of the 20th century. More recently, black holes were once considered to be science fiction. Einstein himself wrote a paper in 1939 that proved that black holes could never form. Yet today, the Hubble Space Telescope and the Chandra X-ray Telescope have revealed thousands of black holes in space. The reason that these technologies were deemed impossibilities is that the basic laws of physics and science were not known in the 19th century and the early part of the 20th. Given the huge gaps in the understanding of science at the time, especially at the atomic level, it's no wonder such advances were considered impossible. Studying the impossible. Ironically, the serious study of the impossible has frequently opened up rich and entirely unexpected domains of science. For example, over the centuries, the frustrating and futile search for a perpetual motion machine led physicists to conclude that such a machine was impossible, forcing them to postulate the conservation of energy and the three laws of thermodynamics. Thus, the futile search to build perpetual motion machines helped to open up an entirely new field of thermodynamics, which in part laid the foundation of the steam engine, the machine age, and the modern industrial society. At the end of the 19th century, scientists decided that it was impossible for the Earth to be billions of years old. Lord Kelvin declared flatly that a molten Earth would cool down in 20 to 40 million years, contradicting the geologists and Darwinian biologists who claimed that the Earth might be billions of years old. The impossible was finally proven to be possible with the discovery of the nuclear force by Madame Curie and others, showing how the center of the Earth, heated by radioactive decay, could indeed be kept molten for billions of years. We ignore the impossible at our peril. In the 1920s and 1930s, Robert Goddard, the father of modern rocketry, was the subject of intense criticism by those who thought that rockets could never travel in outer space. They sarcastically called his pursuit Goddard's folly. In 1921, the editors of the New York Times railed against Dr. Goddard's work. Professor Goddard does not know the relation between action and reaction, and the need to have something better than a vacuum against which to react. He seems to lack the basic knowledge ladled out daily in high schools. Rockets were impossible, the editors huffed, because there was no air to push against in outer space. Sadly, one head of state did understand the implications of Goddard's impossible rockets: Adolf Hitler. During World War II, Germany's barrage of impossibly advanced V-2 rockets rained death and destruction on London, almost bringing it to its knees. Studying the impossible may have also changed the course of world history. In the 1930s, it was widely believed, even by Einstein, that an atomic bomb was impossible. Physicists knew that there was a tremendous amount of energy locked deep inside the atom's nucleus, according to Einstein's equation E equals mc squared. But the energy released by a single nucleus was too insignificant to consider. But atomic physicist Leo Szilard remembered reading the 1914 H.G. Wells novel, The World Set Free, in which Wells predicted the development of the atomic bomb. In the book, he stated that the secret of the atomic bomb would be solved by a physicist in 1933. By chance, Szilard stumbled upon this book in 1932. Spurred on by the novel, in 1933, precisely as predicted by Wells some 2 decades earlier, he hit upon the idea of magnifying the power of a single atom via a chain reaction, so that the energy of splitting a single uranium nucleus could be magnified by many trillions. Szilard then set into motion a series of key experiments and secret negotiations between Einstein and President Franklin Roosevelt that would lead to the Manhattan Project, which built the atomic bomb. Time and again, we see that the study of the impossible has opened up entirely new vistas, pushing the boundaries of physics and chemistry and forcing scientists to redefine what they mean by impossible. As Sir William Osler once said, the philosophies of one age have become the absurdities of the next, and the foolishness of yesterday has become the wisdom of tomorrow. Many physicists subscribe to the famous dictum of T.H. White, who wrote in The Once and Future King, "Anything that is not forbidden is mandatory." In physics, we find evidence of this all the time. Unless there is a law of physics explicitly preventing a new phenomenon, we eventually find that it exists. This has happened several times in the search for new subatomic particles. By probing the limits of what is forbidden, physicists have often unexpectedly discovered new laws of physics. A corollary to T.H. White's statement might well be, anything that is not impossible is mandatory. For example, cosmologist Stephen Hawking tried to prove that time travel was impossible by finding a new law of physics that would forbid it, which he called the chronology protection conjecture. Unfortunately, after many years of hard work, he was unable to prove this principle. In fact, to the contrary, physicists have now demonstrated that a law that prevents time travel is beyond our present-day mathematics. Today, because there is no law of physics preventing the existence of time machines, physicists have had to take their possibility very seriously. The purpose of this book is to consider what technologies are considered impossible today that might well become commonplace decades to centuries down the road. Already one impossible technology is now proving to be possible: the notion of teleportation, at least at the level of atoms. Even a few years ago, physicists would have said that sending or beaming an object from one point to another violated the laws of quantum physics. The writers of the original Star Trek television series, in fact, were so stung by the criticism from physicists that they added Heisenberg compensators to explain their teleporters in order to address this flaw. Today, because of a recent breakthrough, physicists can teleport atoms across a room, or photons under the Danube River. Predicting the future. It is always a bit dangerous to make predictions, especially ones set centuries to thousands of years in the future. The physicist Niels Bohr was fond of saying, "Prediction is very hard to do, especially about the future." But there is a fundamental difference between the time of Jules Verne and the present. Today, the fundamental laws of physics are basically understood. Physicists today understand the basic laws extending over a staggering 43 orders of magnitude, from the interior of the proton out to the expanding universe. As a result, physicists can state, with reasonable confidence, what the broad outlines of future technology might look like, and better differentiate between those technologies that are merely improbable and those that are truly impossible. In this book, therefore, I divide the things that are impossible into 3 categories. The first are what I call Class 1 impossibilities. These are technologies that are impossible today, but that do not violate the known laws of physics. So they might be possible in this century, or perhaps the next, in modified form. They include teleportation, antimatter engines, certain forms of telepathy, psychokinesis, and invisibility. The second category is what I term Class 2 impossibilities. These are technologies that sit at the very edge of our understanding of the physical world. If they are possible at all, they might be realized on a scale of millennia to millions of years in the future. They include time machines, the possibility of hyperspace travel, and travel through wormholes. The final category is what I call Class 3 impossibilities. These are technologies that violate the known laws of physics. Surprisingly, there are very few such impossible technologies. If they do turn out to be possible, they would represent a fundamental shift in our understanding of physics. This classification is significant, I feel, because so many technologies in science fiction are dismissed by scientists as being totally impossible, when what they actually mean is that they are impossible for a primitive civilization like ours. Alien visitations, for example, are usually considered impossible because the distances between the stars are so vast. While interstellar travel for our civilization is clearly impossible, it may be possible for a civilization centuries to thousands or millions of years ahead of ours. So it is important to rank such impossibilities. Technologies that are impossible for our current civilization are not necessarily impossible for other types of civilizations. Statements about what is possible and impossible have to take into account technologies that are millennia to millions of years ahead of ours. Carl Sagan once wrote, "What does it mean for a civilization to be 1,000,000 years old? We have had radio telescopes and spaceships for a few decades. Our technical civilization is a few hundred years old. An advanced civilization, millions of years old, is as much beyond us as we are beyond a bush baby or a macaque." In my own research, I focused professionally on trying to complete Einstein's dream of a theory of everything. Personally, I find it quite exhilarating to work on a final theory that may ultimately answer some of the most difficult, impossible questions in science today, such as whether time travel is possible, what lies at the center of a black hole, or what happened before the Big Bang. I still daydream about my lifelong love affair with the impossible, and wonder when and if some of these impossibilities might enter the ranks of the everyday. Part 1. Class 1 Impossibilities. Chapter 1. Force Fields. 1. When a distinguished but elderly scientist states that something is possible, he is almost certainly right. When he states that something is impossible, he is very probably wrong. 2. The only way of discovering the limits of the possible is to venture a little way past them into the impossible. 3. Any sufficiently advanced technology is indistinguishable from magic. Arthur C. Clarke's 3 Laws. Shields up. In countless Star Trek episodes, this is the first order that Captain Kirk barks out to the crew, raising the force fields to protect the Starship Enterprise against enemy fire. So vital are force fields in Star Trek that the tide of the battle can be measured by how the force field is holding up. Whenever power is drained from the force fields, the Enterprise suffers more and more damaging blows to its hull, until finally surrender is inevitable. So what is a force field? In science fiction, it's deceptively simple. A thin, invisible, yet impenetrable barrier, able to deflect lasers and rockets alike. At first glance, a force field looks so easy that its creation as a battlefield shield seems imminent. One expects that any day, some enterprising inventor will announce the discovery of a defensive force field. But the truth is far more complicated. In the same way that Edison's light bulb revolutionized modern civilization, a force field could profoundly affect every aspect of our lives. The military could use force fields to become invulnerable, creating an impenetrable shield against enemy missiles and bullets. Bridges, superhighways, and roads could in theory be built by simply pressing a button. Entire cities could sprout instantly in the desert, with skyscrapers made entirely of force fields. Force fields erected over cities could enable their inhabitants to modify the effects of their weather, high winds, blizzards, tornadoes, at will. Cities could be built under the oceans, within the safe canopy of a force field. Glass, steel, and mortar could be entirely replaced. Yet, oddly enough, a force field is perhaps one of the most difficult devices to create in the laboratory. In fact, some physicists believe it might actually be impossible without modifying its properties. Michael Faraday. The concept of force fields originates from entire cities and changed the course of world civilization. The key to Faraday's greatest discoveries was his force fields. If one places iron filings over a magnet, one finds that the iron filings create a spiderweb-like pattern that fills up all of space. These are Faraday's lines of force, which graphically describe how the force fields of electricity and magnetism permeate space. If one graphs the magnetic fields of the Earth, for example, one finds that the lines emanate from the North Polar region and then fall back to the Earth in the South Polar region. Similarly, if one were to graph the electric field lines of a lightning rod in a thunderstorm, one would find that the lines of force concentrate at the tip of the lightning rod. Empty space, to Faraday, was not empty at all, but was filled with lines of force that could make distant objects move. Because of Faraday's poverty-stricken youth, he was illiterate in mathematics, and as a consequence, his notebooks are full not of equations, but of hand-drawn diagrams of these lines of force. Ironically, his lack of mathematical training led him to create the beautiful diagrams of lines of force that now can be found in any physics textbook. In science, a physical picture is often more important than the mathematics used to describe it. Historians have speculated on how Faraday was led to his discovery of force fields, one of the most important concepts in all of science. In fact, the sum total of all modern physics is written in the language of Faraday's fields. In 1831, he made the key breakthrough regarding force fields that changed civilization forever. One day, he was moving a child's magnet over a coil of wire, and he noticed that he was able to generate an electric current in the wire without ever touching it. This meant that a magnet's invisible field could push electrons in a wire across empty space, creating a current. Faraday's force fields, which were previously thought to be useless, idle doodlings, were real, material forces that could move objects and generate power. Today, the light that you are using to read this page is probably energized by Faraday's discovery about electromagnetism. A spinning magnet creates a force field that pushes the electrons in a wire, causing them to move in an electrical current. This electricity in the wire can then be used to light up a light bulb. This same principle is used to generate electricity to power the cities of the world. Water flowing across a dam, for example, causes a huge magnet in a turbine to spin, which then pushes the electrons in a wire, forming an electric current that is sent across high-voltage wires into our homes. In other words, the force fields of Michael Faraday are the forces that drive modern civilization, from electric bulldozers to today's computers, internet, and iPods. Faraday's force fields have been an inspiration for physicists for a century and a half. Einstein was so inspired by them that he wrote his theory of gravity in terms of force fields. I, too, was inspired by Faraday's work. Years ago, I successfully wrote the theory of strings in terms of the force fields of Faraday, thereby founding string field theory. In physics, when someone says, He thinks like a line of force. It is meant as a great compliment. The Four Forces. Over the last 2,000 years, one of the crowning achievements of physics has been the isolation and identification of the four forces that rule the universe. All of them can be described in the language of fields introduced by Faraday. Unfortunately, however, none of them has quite the properties of the force fields described in most science fiction. These forces are: 1. Gravity, the silent force that keeps our feet on the ground, prevents the Earth and the stars from disintegrating, and holds the solar system and galaxy together. Without gravity, we would be flung off the Earth into space at a rate of 1,000 miles per hour by the spinning planet. The problem is that gravity has precisely the opposite properties of a force field found in science fiction. Gravity is attractive, not repulsive, is extremely weak, relatively speaking, and works over enormous astronomical distances. In other words, it is almost the opposite of the flat, thin, impenetrable barrier that one reads about in science fiction or one sees in science fiction movies. For example, it takes the entire planet Earth to attract a feather to the floor, but we can counteract Earth's gravity by lifting the feather with a finger. The action of our finger can counteract the gravity of an entire planet that weighs over 6 trillion kilograms. 2. Electromagnetism, EM, the force that lights up our cities. Lasers, radio, TV, modern electronics, computers, the internet, electricity, magnetism, all are consequences of the electromagnetic force. It is perhaps the most useful force ever harnessed by humans. Unlike gravity, it can be both attractive and repulsive. However, there are several reasons that it is unsuitable as a force field. First, it can be easily neutralized. Plastics and other insulators, for example, can easily penetrate a powerful electric or magnetic field. A piece of plastic thrown in a magnetic field would pass right through. Second, electromagnetism acts over large distances and cannot easily be focused onto a plane. The laws of the EM force are described by James Clerk Maxwell's equations, and these equations do not seem to admit force fields as solutions. 3 and 4. The weak and strong nuclear forces. The weak force is the force of radioactive decay. It is the force that heats up the center of the Earth, which is radioactive. It is the force behind volcanoes, earthquakes, and continental drift. The strong force holds the nucleus of the atom together. The energy of the sun and the stars originates from the nuclear force, which is responsible for lighting up the universe. The problem is that the nuclear force is a short-range force, acting mainly over the distance of a nucleus. Because it is bound to the properties of nuclei, it is extremely hard to manipulate. At present, the only ways we have of manipulating this force are to blow subatomic particles apart in atom smashers or to detonate atomic bombs. Although the force fields used in science fiction may not conform to the known laws of physics, there are still loopholes that might make the creation of such a force field possible. First, there may be a fifth force still unseen in the laboratory. Such a force might, for example, work over a distance of only a few inches to feet, rather than over astronomical distances. Initial attempts to measure the presence of such a fifth force, however, have yielded negative results. Second, it may be possible to use a plasma to mimic some of the properties of a force field. A plasma is the fourth state of matter. Solids, liquids, and gases make up the 3 familiar states of matter, but the most common form of matter in the universe is plasma, a gas of ionized atoms. Because the atoms of a plasma are ripped apart, with electrons torn off the atoms are electrically charged and can be easily manipulated by electric and magnetic fields. Plasmas are the most plentiful form of visible matter in the universe, making up the sun, the stars, and interstellar gas. Plasmas are not familiar to us because they are only rarely found on the Earth. But we can see them in the form of lightning bolts, the sun, and the interior of your plasma TV. Plasma windows. As noted above, if a gas is heated to a high enough temperature, thereby creating a plasma, it can be molded and shaped by magnetic and electrical fields. It can, for example, be shaped in the form of a sheet or window. Moreover, this plasma window can be used to separate a vacuum from ordinary air. In principle, one might be able to prevent the air within a spaceship from leaking out into space, thereby creating a convenient, transparent interface between outer space and the spaceship. In the Star Trek TV series, such a force field is used to separate the shuttle bay, containing small shuttlecraft, from the vacuum of outer space. Not only is it a clever way to save money on props, but it is a device that is possible. The plasma window was invented by physicist A.D. Hershkovich in 1995 at the Brookhaven National Laboratory in Long Island, New York. He developed it to solve the problem of how to weld metals using electron beams. A welder's acetylene torch uses a blast of hot gas to melt and then weld metal pieces together. But a beam of electrons can weld metals faster, cleaner, and more cheaply than ordinary methods. The problem with electron beam welding, however, is that it needs to be done in a vacuum. This requirement is quite inconvenient because it means creating a vacuum box that may be as big as an entire room. Dr. Hershkovich invented the plasma window to solve this problem. Only 3 feet high and less than 1 foot in diameter, the plasma window heats gas to 12,000 degrees Fahrenheit, creating a plasma that is trapped by electric and magnetic fields. These particles exert pressure, as in any gas, which prevents air from rushing into the vacuum chamber, thus separating air from the vacuum. When one uses argon gas in the plasma window, it glows blue, like the force field in Star Trek. The plasma window has wide applications for space travel and industry. Many times, manufacturing processes need a vacuum to perform microfabrication and dry etching for industrial purposes. But working in a vacuum can be expensive. But with the plasma window, one can cheaply contain a vacuum with the flick of a button. But can the plasma window also be used as an impenetrable shield? Can it withstand a blast from a cannon? In the future, one can imagine a plasma window of much greater power and temperature, sufficient to damage or vaporize incoming projectiles. But to create a more realistic force field, like that found in science fiction, one would need a combination of several technologies stacked in layers. Each layer might not be strong enough alone to stop a cannonball, but the combination might suffice. The outer layer could be a supercharged plasma window, heated to temperatures high enough to vaporize metals. A second layer could be a curtain of high-energy laser beams. This curtain, containing thousands of crisscrossing laser beams, would create a lattice that would heat up objects that pass through it, effectively vaporizing them. I will discuss lasers further in the next chapter. And behind this laser curtain, one might envision a lattice made of carbon nanotubes, tiny tubes made of individual carbon atoms that are 1 atom thick and that are many times stronger than steel. Although the current world record for a carbon nanotube is only about 15 millimeters long, one can envision a day when we might be able to create carbon nanotubes of arbitrary length. Assuming that carbon nanotubes can be woven into a lattice, they could create a screen of enormous strength, capable of repelling most objects. The screen would be invisible, since each carbon nanotube is atomic in size, but the carbon nanotube lattice would be stronger than any ordinary material. So, via a combination of plasma window, laser curtain, and carbon nanotube screen, one might imagine creating an invisible wall that would be nearly impenetrable by most means. Yet even this multi-layered shield would not completely fulfill all the properties of a science fiction force field, because it would be transparent and therefore incapable of stopping a laser beam. In a battle with laser cannons, the multi-layered shield would be useless. To stop a laser beam, the shield would also need to possess an advanced form of photochromatics. This is the process used in sunglasses that darken by themselves upon exposure to UV radiation. Photochromatics are based on molecules that can exist in at least two states. In one state, the molecule is transparent, but when it is exposed to UV radiation, it instantly changes to the second form, which is opaque. One day, we might be able to use nanotechnology to produce a substance as tough as carbon nanotubes that can change its optical properties when exposed to laser light. In this way, a shield might be able to stop a laser blast, as well as a particle beam or cannon fire. At present, however, photochromatics that can stop laser beams do not exist. Magnetic levitation. In science fiction, force fields have another purpose besides deflecting ray gun blasts, and that is to serve as a platform to defy gravity. In the movie Back to the Future, Michael J. Fox rides a hoverboard, which resembles a skateboard, except that it floats over the street. Such an anti-gravity device is impossible given the laws of physics as we know them today, as we will see in Chapter 10. But magnetically enhanced hoverboards and hover cars could become a reality in the future, giving us the ability to levitate large objects at will. In the future, if room temperature superconductors become a reality, one might be able to levitate objects using the power of magnetic force fields. If we place two bar magnets next to each other, with north poles opposite each other, the two magnets repel each other. If we rotate the magnet so that the north pole is close to the other south pole, then the two magnets attract each other. This same principle, that north poles repel each other, can be used to lift enormous weights off the ground. Already, several nations are building advanced magnetic levitation trains, maglev trains, that hover just above the railroad tracks using ordinary magnets. Because they have zero friction, they can attain record-breaking speeds, floating over a cushion of air. In 1984, the world's first commercial automated maglev system began operation in the United Kingdom, running from Birmingham International Airport to the nearby Birmingham International Railway Station. Maglev trains have also been built in Germany, Japan, and Korea, although most of them have not been designed for high velocities. The first commercial maglev train, operating at high velocities, is the Initial Operating Segment, IOS, demonstration line in Shanghai, which travels at a top speed of 268 miles per hour. The Japanese maglev train in Yamanashi Prefecture attained a velocity of 361 miles per hour, even faster than the usual wheeled trains. But these maglev devices are extremely expensive. One way to increase efficiency would be to use superconductors, which lose all electrical resistance when they are cooled down to near absolute zero. Superconductivity was discovered in 1911 by Heike Onnes. If certain substances are cooled to below 20 Kelvin above absolute zero, all electrical resistance is lost. Usually when we cool down the temperature of a metal, its resistance decreases gradually. This is because random vibrations of the atom impede the flow of electrons in a wire. By reducing the temperature, these random motions are reduced, and hence electricity flows with less resistance. But much to Onnes' surprise, he found that the resistance of certain materials fell abruptly to zero at a critical temperature. Physicists immediately recognized the importance of this result. Power lines lose a significant amount of energy by transporting electricity across long distances. But if all resistance could be eliminated, electrical power could be transmitted almost for free. In fact, if electricity were made to circulate in a coil of wire, the electricity would circulate for millions of years without any reduction in energy. Furthermore, magnets of incredible power could be made with little effort from these enormous electric currents. With these magnets, one could lift huge loads with ease. Despite all these miraculous powers, the problem with superconductivity is that it is very expensive to immerse large magnets in vats of supercooled liquid. Huge refrigeration plants are required to keep liquids supercooled, making superconducting magnets prohibitively expensive. But one day, physicists may be able to create a room temperature superconductor, the holy grail of solid-state physicists. The invention of room temperature superconductors in the laboratory would spark a second industrial revolution. Powerful magnetic fields capable of lifting cars and trains would become so cheap that hover cars might become economically feasible. With room temperature superconductors, the fantastic flying cars seen in Back to the Future, Minority Report, and Star Wars might become a reality. In principle, one might be able to wear a belt made of superconducting magnets that would enable one to effortlessly levitate off the ground. With such a belt, one could fly in the air like Superman. Room temperature superconductors are so remarkable that they appear in numerous science fiction novels, such as the Ringworld series, written by Larry Niven in 1970. For decades, physicists have searched for room temperature superconductors without success. It has been a tedious hit-or-miss process, testing one material after another. But in 1986, a new class of substances called high-temperature superconductors was found that became superconductors at about 90 degrees above absolute zero, or 90 Kelvin, creating a sensation in the world of physics. The floodgates seemed to open. Month after month, physicists raced one another to break the next world's record for a superconductor. For a brief moment, it seemed as if the possibility of room temperature superconductors would leap off the pages of science fiction novels and into our living rooms. But after a few years of moving at breakneck speed, research in high-temperature superconductors began to slow down. At present, the world's record for a high-temperature superconductor is held by a substance called mercury, thallium, barium, calcium, copper oxide, which becomes superconducting at 138 Kelvin, or minus 135 degrees Celsius. This relatively high temperature is still a long way from room temperature, but this 138 Kelvin record is still important. Nitrogen liquefies at 77 Kelvin, and liquid nitrogen costs about as much as ordinary milk. Hence, ordinary liquid nitrogen could be used to cool down these high-temperature superconductors rather cheaply. Of course, room temperature superconductors would need no cooling whatsoever. Embarrassingly enough, at present there is no theory explaining the properties of these high-temperature superconductors. In fact, a Nobel Prize is awaiting the enterprising physicist who can explain how high-temperature superconductors work. These high-temperature superconductors are made of atoms arranged in distinctive layers. Many physicists theorize that this layering of the ceramic material makes it possible for electrons to flow freely within each layer, creating a superconductor. But precisely how this is done is still a mystery. Because of this lack of knowledge, physicists unfortunately resort to a hit-or-miss procedure to search for new high-temperature superconductors. This means that the fabled room temperature superconductor may be discovered tomorrow, next year, or not at all. No one knows when or if such a substance will ever be found. But if room temperature superconductors are discovered, a tidal wave of commercial applications could be set off. Magnetic fields that are 1,000,000 times more powerful than the Earth's magnetic field, which is 0.5 Gauss, might become commonplace. One common property of superconductivity is called the Meissner effect. If you place a magnet above a superconductor, the magnet will levitate, as if held upward by some invisible force. The reason for the Meissner effect is that the magnet has the effect of creating a mirror image magnet within the superconductor, so that the original magnet and the mirror image magnet repel each other. Another way to see this is that magnetic fields cannot penetrate into a superconductor. Instead, magnetic fields are expelled. So if a magnet is held above a superconductor, its lines of force are expelled by the superconductor, and the lines of force then push the magnet upward, causing it to levitate. Using the Meissner effect, one can imagine a future in which the highways are made of these special ceramics. Then magnets, placed in our belts or our tires, could enable us to magically float to our destination without any friction or energy loss. The Meissner effect works only on magnetic materials, such as metals, but it is also possible to use superconducting magnets to levitate non-magnetic materials, called paramagnets or diamagnets. These substances do not have magnetic properties of their own. They acquire their magnetic properties only in the presence of an external magnetic field. Paramagnets are attracted by an external magnet, while diamagnets are repelled by an external magnet. Water, for example, is a diamagnet. Since all living things are made of water, they can levitate in the presence of a powerful magnetic field. In a magnetic field of about 15 teslas, 30,000 times the Earth's field, scientists have levitated small animals, such as frogs. But if room temperature superconductors become a reality, it should be possible to levitate large non-magnetic objects as well, via their diamagnetic property. In conclusion, force fields as commonly described in science fiction do not fit the description of the four forces of the universe. Yet it may be possible to simulate many of the properties of force fields by using a multi-layered shield consisting of plasma windows, laser curtains, carbon nanotubes, and photochromatics. But developing such a shield could be many decades or even a century away. And if room temperature superconductors can be found, one might be able to use powerful magnetic fields to levitate cars and trains and soar in the air, as in science fiction movies. Given these considerations, I would classify force fields as a Class 1 impossibility. That is, something that is impossible by today's technology, but possible, in modified form, within a century or so. Chapter 2. Invisibility. You cannot depend on your eyes when your imagination is out of focus. Mark Twain. In Star Trek IV, The Voyage Home, a Klingon battlecruiser is hijacked by the crew of the Enterprise. Unlike the starships in the Federation Starfleet, the starships of the Klingon Empire have a secret cloaking device that renders them invisible to light or radar, so that Klingon ships can sneak up behind Federation starships and ambush them with impunity. This cloaking device has given the Klingon Empire a strategic advantage over the Federation of Planets. Is such a device really possible? Invisibility has long been one of the marvels of science fiction and fantasy, from the pages of The Invisible Man to the magic invisibility cloak of the Harry Potter books, or the ring in The Lord of the Rings. Yet for at least a century, physicists have dismissed the possibility of invisibility cloaks, stating flatly that they are impossible. They violate the laws of optics and do not conform to any of the known properties of matter. But today, the impossible may become possible. New advances in metamaterials are forcing a major revision of optics textbooks. Working prototypes of such materials have actually been built in the laboratory, sparking intense interest by the media, industry, and the military in making the visible become invisible. Invisibility throughout history. Invisibility is perhaps one of the oldest concepts in ancient mythology. Since the advent of recorded history, people who have been alone on a creepy night have been frightened by the invisible spirits of the dead, the souls of the long-departed lurking in the dark. The Greek hero Perseus was able to slay the evil Medusa, armed with a helmet of invisibility. Military generals have dreamed of an invisibility cloaking device. Being invisible, one could easily penetrate enemy lines and capture the enemy by surprise. Criminals could use invisibility to pull off spectacular robberies. Invisibility played a central part in Plato's theory of ethics and morality. In his philosophical masterpiece, The Republic, Plato recounts the myth of the Ring of Gyges. The poor but honest shepherd Gyges of Lydia enters a hidden cave and finds a tomb containing a corpse wearing a golden ring. Gyges discovers that this golden ring has the magical power to make him invisible. Soon this poor shepherd is intoxicated with the power this ring gives him. After sneaking into the king's palace, Gyges uses his power to seduce the queen, and with her help, murder the king and become the next king of Lydia. The moral that Plato wished to draw out is that no man can resist the temptation of being able to steal and kill at will. All men are corruptible. Morality is a social construct imposed from the outside. A man may appear to be moral in public, to maintain his reputation for integrity and honesty, but once he possesses the power of invisibility, the use of such power would be irresistible. Some believe that this morality tale was the inspiration for J.R.R. Tolkien's Lord of the Rings trilogy, in which a ring that grants the wearer invisibility is also a source of evil. Invisibility is also a common plot device in science fiction. In the Flash Gordon series of the 1930s, Flash becomes invisible in order to escape the firing squad of Ming the Merciless. In the Harry Potter novels and movies, Harry dons a special cloak that allows him to roam Hogwarts Castle undetected. H.G. Wells put much of this mythology into concrete form with his classic novel The Invisible Man, in which a medical student accidentally discovers the power of the fourth dimension and becomes invisible. Unfortunately, he uses this fantastic power for private gain, starts a wave of petty crimes, and eventually dies desperately trying to evade the police. Maxwell's equations and the secret of light. It was not until the work of Scottish physicist James Clerk Maxwell, one of the giants of 19th century physics, that physicists had a firm understanding of the laws of optics. Maxwell, in some sense, was the opposite of Michael Faraday. Whereas Faraday had superb experimental instincts, but no formal training whatsoever, Maxwell, a contemporary of Faraday, was a master of advanced mathematics. He excelled as a student of mathematical physics at Cambridge, where Isaac Newton had done his work 2 centuries earlier. Newton had invented the calculus, which was expressed in the language of differential equations, which describe how objects smoothly undergo infinitesimal changes in space and time. The motion of ocean waves, fluids, gases, and cannonballs could all be expressed in the language of differential equations. Maxwell set out with a clear goal to express the revolutionary findings of Faraday and his force fields through precise differential equations. Maxwell began with Faraday's discovery that electric fields could turn into magnetic fields and vice versa. He took Faraday's depictions of force fields and rewrote them in the precise language of differential equations, producing one of the most important series of equations in modern science. They are a series of 8 fierce-looking differential equations. Every physicist and engineer in the world has to sweat over them when mastering electromagnetism in graduate school. Next, Maxwell asked himself the fateful question: if magnetic fields can turn into electric fields and vice versa, what happens if they are constantly turning into each other in a never-ending pattern? Maxwell found that these electric magnetic fields would create a wave, much like an ocean wave. To his astonishment, he calculated the speed of these waves and found it to be the speed of light. In 1864, upon discovering this fact, he wrote prophetically, "This velocity is so nearly that of light that it seems we have strong reason to conclude that light itself is an electromagnetic disturbance." It was perhaps one of the greatest discoveries in human history. For the first time, the secret of light was finally revealed. Maxwell suddenly realized that everything, from the brilliance of the sunrise, the blaze of the setting sun, the dazzling colors of the rainbow, and the firmament of stars in the heavens, could be described by the waves he was scribbling on a sheet of paper. Today, we realize that the entire electromagnetic spectrum, from radar to TV, infrared light, visible light, ultraviolet light, X-rays, microwaves, and gamma rays, is nothing but Maxwell waves, which in turn are vibrating Faraday force fields. Commenting on the importance of Maxwell's equations, Einstein wrote that they are the most profound and the most fruitful that physics has experienced since the time of Newton. Tragically, Maxwell, one of the greatest physicists of the 19th century, died at the early age of 48 of stomach cancer, probably the very same disease that killed his mother at the same age. If he had lived longer, he might have discovered that his equations allowed for distortions of space-time that would lead directly to Einstein's relativity theory. It is staggering to realize that relativity might possibly have been discovered at the time of the American Civil War had Maxwell lived longer. Maxwell's theory of light and the atomic theory give simple explanations for optics and invisibility. In a solid, the atoms are tightly packed, while in a liquid or gas, the molecules are spaced much farther apart. Most solids are opaque because light rays cannot pass through the dense matrix of atoms in a solid, which act like a brick wall. Many liquids and gases, by contrast, are transparent because light can pass more readily between the large spaces between their atoms, a space that is larger than the wavelength of visible light. For example, water, alcohol, ammonia, acetone, hydrogen peroxide, gasoline, and so forth are all transparent, as are gases such as oxygen, hydrogen, nitrogen, carbon dioxide, methane, and so on. There are some important exceptions to this rule. Many crystals are both solid and transparent, but the atoms of a crystal are arranged in a precise lattice structure, stacked in regular rows, with regular spacing between them. Hence, there are many pathways that a light beam can take through a crystalline lattice. Therefore, although a crystal is as tightly packed as any solid, light can still work its way through the crystal. Under certain circumstances, a solid object may become transparent if the atoms are arranged randomly. This can be done by heating certain materials to a high temperature and then rapidly cooling them. Glass, for example, is a solid with many properties of a liquid because of the random arrangement of its atoms. Certain candies can become transparent via this method as well. Clearly, invisibility is a property that arises at the atomic level via Maxwell's equations, and hence would be exceedingly difficult, if not impossible, to duplicate using ordinary means. To make Harry Potter invisible, one would have to liquefy him, boil him to create steam, crystallize him, heat him again, and then cool him off, all of which would be quite difficult to accomplish, even for a wizard. The military, unable to create invisible airplanes, has tried to do the next best thing, create stealth technology, which renders airplanes invisible to radar. Stealth technology relies on Maxwell's equations to create a series of tricks. A stealth fighter jet is perfectly visible to the human eye, but its radar image on an enemy radar screen is only the size of a large bird. Stealth technology is actually a hodgepodge of tricks. By changing the materials within the jet fighter, reducing its steel content and using plastics and resins instead, changing the angles of its fuselage, rearranging its exhaust pipes, and so on, one can make enemy radar beams hitting the craft disperse in all directions, so they never get back to the enemy radar screen. Even with stealth technology, a jet fighter is not totally invisible. Rather, it has deflected and dispersed as much radar as is technically possible. Metamaterials and invisibility. But perhaps the most promising new development involving invisibility is an exotic new material called a metamaterial, which may one day render objects truly invisible. Ironically, the creation of metamaterials was once thought to be impossible because they violated the laws of optics. But in 2006, researchers at Duke University in Durham, North Carolina, and Imperial College in London successfully defied conventional wisdom and used metamaterials to make an object invisible to microwave radiation. Although there are still many hurdles to overcome, for the first time in history, we now have a blueprint to render ordinary objects invisible. The Pentagon's Defense Advanced Research Projects Agency, DARPA, funded this research. Nathan Myhrvold, former Chief Technology Officer at Microsoft, says the revolutionary potential of metamaterials will completely change the way we approach optics and nearly every aspect of electronics. Some of these metamaterials can perform feats that would have seemed miraculous a few decades ago. What are these metamaterials? They are substances that have optical properties not found in nature. Metamaterials are created by embedding tiny implants within a substance that force electromagnetic waves to bend in unorthodox ways. At Duke University, scientists embedded tiny electrical circuits within copper bands that are arranged in flat concentric circles. somewhat resembling the coils of an electric oven. The result was a sophisticated mixture of ceramic, Teflon, fiber composites, and metal components. These tiny implants in the copper make it possible to bend and channel the path of microwave radiation in a specific way. Think about the way a river flows around a boulder. Because the water quickly wraps around the boulder, the presence of the boulder has been washed out downstream. Similarly, metamaterials can continuously alter and bend the path of microwaves, so that they flow around a cylinder, for example, essentially making everything inside the cylinder invisible to microwaves. If the metamaterial can eliminate all reflection and shadows, then it can render an object totally invisible to that form of radiation. Scientists successfully demonstrated this principle with a device made of 10 fiberglass rings covered with copper elements. A copper ring inside the device was rendered nearly invisible to microwave radiation, casting only a minuscule shadow. At the heart of metamaterials is their ability to manipulate something called the index of refraction. Refraction is the bending of light as it moves through transparent media. If you put your hand in water or look through the lens of your glasses, you notice that water and glass distort and bend the path of ordinary light. The reason that light bends in glass or water is that light slows down when it enters a dense transparent medium. The speed of light in a pure vacuum always remains the same, but light traveling through glass or water must pass through trillions of atoms and hence slows down. The speed of light divided by the slower speed of light inside the medium is called the index of refraction. Since light slows down in glass, the index of refraction is always greater than 1.0. For example, the index of refraction is 1.00 for a vacuum, 1.0003 for air, 1.5 for glass, and 2.4 for diamond. Usually, the denser the medium, the greater the degree of bending, and the greater the index of refraction. A familiar example of the index of refraction is a mirage. If you are driving on a hot day and look straight toward the horizon, the road may seem to be shimmering, creating the illusion of a glistening lake. In the desert, one can sometimes see the outlines of distant cities and mountains on the horizon. This is because hot air rising from the pavement or desert has a lower density than normal air, and hence a lower index of refraction than the surrounding colder air, and therefore light from distant objects can be refracted off the pavement into your eye, giving you the illusion that you are seeing distant objects. Usually, the index of refraction is a constant. A narrow beam of light is bent when it enters glass and then keeps going in a straight line. But assume for the moment that you could control the index of refraction at will, so that it could change continuously at every point in the glass. As light moved in this new material, light could bend and meander in new directions, creating a path that would wander throughout the substance like a snake. If one could control the index of refraction inside a metamaterial so that light passed around an object, then the object would become invisible. To do this, this metamaterial must have a negative index of refraction, which every optics textbook says is impossible. Metamaterials were first theorized in a paper by Soviet physicist Viktor Veselago in 1967 and were shown to have weird optical properties, such as a negative refractive index and reverse Doppler effect. Metamaterials are so bizarre and preposterous that they were once thought to be impossible to construct. But in the last few years, metamaterials have actually been manufactured in the laboratory, forcing reluctant physicists to rewrite all the textbooks on optics. Researchers in metamaterials are constantly pestered by journalists who wish to know when invisibility cloaks will hit the market. The answer is, not anytime soon. David Smith of Duke University says, "Reporters, they call up and they just want you to say a number of months, number of years. They push and push and push, and you finally say, well, maybe 15 years. Then you've got your headline, right? 15 years till Harry Potter's cloak." That's why he now declines to give any specific timetable. Fans of Harry Potter or Star Trek may have to wait. While a true invisibility cloak is possible within the laws of physics, as most physicists will agree, formidable technical hurdles remain before this technology can be extended to work with visible light rather than just microwave radiation. In general, the internal structures implanted inside the metamaterial must be smaller than the wavelength of the radiation. For example, microwaves can have a wavelength of about 3 centimeters. So for a metamaterial to bend the path of microwaves, it must have tiny implants embedded inside it that are smaller than 3 centimeters. But to make an object invisible to green light with a wavelength of 500 nanometers, the metamaterial must have structures embedded within it that are only about 50 nanometers long, and nanometers are atomic length scales requiring nanotechnology. 1 nanometer is a billionth of a meter in length. Approximately 5 atoms can fit within a single nanometer. This is perhaps the key problem we face in our attempts to create a true invisibility cloak. The individual atoms inside a metamaterial would have to be modified to bend a light beam like a snake. Metamaterials for visible light. The race is on. Ever since the announcement that metamaterials have been fabricated in the laboratory, there's been a stampede of activity in this area, with new insights and startling breakthroughs coming every few months. The goal is clear: to use nanotechnology to create metamaterials that can bend visible light, not just microwaves. Several approaches have been proposed, all of them quite promising. One proposal is to use off-the-shelf technology, that is, to borrow known techniques from the semiconductor industry to create new metamaterials. A technique called photolithography lies at the heart of computer miniaturization, and hence drives the computer revolution. This technology enables engineers to place hundreds of millions of tiny transistors onto a silicon wafer no bigger than your thumb. The reason that computer power doubles every 18 months, which is called Moore's Law, is because scientists use ultraviolet radiation to etch tinier and tinier components onto a silicon chip. This technique is very similar to the way in which stencils are used to create colorful T-shirts. Computer engineers start with a thin wafer and then apply extremely thin coatings of various materials on top. A plastic mask is then placed over the wafer, which acts as a template. It contains the complex outlines of the wires, transistors, and computer components that are the basic skeleton of the circuitry. The wafer is then bathed in ultraviolet radiation, which has a very short wavelength, and that radiation imprints the pattern onto the photosensitive wafer. By treating the wafer with special gases and acids, the complex circuitry of the mask is etched onto the wafer where it was exposed to ultraviolet light. This process creates a wafer containing hundreds of millions of tiny grooves, which form the outlines of the transistors. At present, the smallest components that one can create with this etching process are about 30 nanometers, or about 150 atoms across. A milestone in the quest for invisibility came when this silicon wafer etching technology was used by a group of scientists to create the first metamaterial that operates in the visible range of light. Scientists in Germany and at the U.S. Department of Energy announced in early 2007 that for the first time in history, they had fabricated a metamaterial that worked for red light. The impossible had been achieved in a remarkably short time. Physicist Kostas Tsoukalis of the Ames Laboratory in Iowa, with Stefan Linden, Martin Wegener, and Gunnar Dahling of the University of Karlsruhe, Germany, were able to create a metamaterial that had an index of -0.6 for red light, at a wavelength of 780 nanometers. Previously, the world record for radiation bent by a metamaterial was 1,400 nanometers, which put it outside the range of visible light, in the range of infrared. The scientists first started with a glass sheet, and then deposited a thin coating of silver, magnesium fluoride, and then another layer of silver, forming a sandwich of fluoride that was only 100 nanometers thick. Then, using standard etching techniques, they created a large array of microscopic square holes in the sandwich, creating a grid pattern resembling a fishnet. The holes are only 100 nanometers wide, much smaller than the wavelength of red light. Then they passed a red light beam through the material and measured its index, which was negative 0.6. These physicists foresee many applications of this technology. Metamaterials may one day lead to the development of a type of flat superlens that operates in the visible spectrum, says Dr. Tsoukalis. Such a lens would offer superior resolution over conventional technology, capturing details much smaller than one wavelength of light. The immediate application of such a superlens would be to photograph microscopic objects with unparalleled clarity, such as the inside of a living human cell, or to diagnose diseases in a baby inside the womb. Ideally, one would be able to obtain photographs of the components of a DNA molecule without having to use clumsy X-ray crystallography. So far, these scientists have demonstrated a negative index of refraction only for red light. Their next step would be to use this technology to create a metamaterial that would bend red light entirely around an object, rendering it invisible to that light. Future developments along these lines may occur in the area of photonic crystals. The goal of photonic crystal technology is to create a chip that uses light rather than electricity to process information. This entails using nanotechnology to etch tiny components onto a wafer, such that the index of refraction changes with each component. Transistors using light have several advantages over those using electricity. For example, there is much less heat loss for photonic crystals. In advanced silicon chips, the heat generated is enough to fry an egg. Thus, they must be continually cooled down, or else they will fail, and keeping them cool is very costly. Not surprisingly, the science of photonic crystals is ideally suited for metamaterials, since both technologies involve manipulating the index of refraction of light at the nanoscale. Invisibility via plasmonics. Not to be outdone, yet another group announced in mid-2007 that they have created a metamaterial that bends visible light using an entirely different technology called plasmonics. Physicists Henri Lezac, Jennifer Dion, and Harry Atwater at the California Institute of Technology announced that they had created a metamaterial that had a negative index for the more difficult blue-green region of the visible spectrum of light. The goal of plasmonics is to squeeze light, so that one can manipulate objects at the nanoscale, especially on the surface of metals. The reason metals conduct electricity is that electrons are loosely bound to metal atoms, so they can freely move along the surface of the metal lattice. The electricity flowing in the wires in your home represents the smooth flow of these loosely bound electrons on the metal surface. But under certain conditions, when a light beam collides with the metal surface, the electrons can vibrate in unison with the original light beam, creating wave-like motions of the electrons on the metal surface, called plasmons, and these wave-like motions beat in unison with the original light beam. More important, one can squeeze these plasmons so that they have the same frequency as the original beam, and hence carry the same information, but have a much smaller wavelength. In principle, one might then cram these squeezed waves onto nanowires. As with photonic crystals, the ultimate goal of plasmonics is to create computer chips that compute using light rather than electricity. The Caltech group built their metamaterial out of 2 layers of silver, with a silicon-nitrogen insulator in between, with a thickness of only 50 nanometers, which acted as a wave guide that could shepherd the direction of the plasmonic waves. Laser light enters and exits the apparatus via 2 slits carved into the metamaterial. By analyzing the angles at which the laser light is bent as it passes through the metamaterial, one can then verify that the light is being bent via a negative index. The future of metamaterials. Progress in metamaterials will accelerate in the future for the simple reason that there is already intense interest in creating transistors that use light beams rather than electricity. Research in invisibility can therefore piggyback on the ongoing research in photonic crystals and plasmonics for creating replacements for the silicon chip. Already hundreds of millions of dollars are being invested in creating replacements for silicon technology, and research in metamaterials will benefit from these research efforts. With breakthroughs occurring in this field every few months, it's not surprising that some physicists see some sort of practical invisibility shield emerging out of the laboratory perhaps within a few decades. In the next few years, for example, scientists are confident that they will be able to create metamaterials that can render an object totally invisible for one frequency of visible light, at least in 2 dimensions. To do this would require embedding tiny nano implants not in regular arrays, but in sophisticated patterns so that light would bend smoothly around an object. Next, scientists will have to create metamaterials that can bend light in 3 dimensions, not just for flat 2-dimensional surfaces. Photolithography has been perfected for making flat silicon wafers, but creating 3-dimensional metamaterials will require stacking wafers in a complex fashion. After that, scientists will have to solve the problem of creating metamaterials that can bend not just one frequency, but many. This will be perhaps the most difficult task, since the tiny implants that have been devised so far bend light of only one precise frequency. Scientists may have to create metamaterials based on layers, with each layer bending a specific frequency. The solution to this problem is not clear. Nevertheless, once an invisibility shield is finally made, it might be a clunky device. Harry Potter's cloak was made of thin, flexible cloth and rendered anyone draped inside invisible. But for this to be possible, the index of refraction inside the cloth would have to be constantly changing in complex ways as it fluttered, which is impractical. More than likely, a true invisibility cloak would have to be made of a solid cylinder of metamaterials, at least initially. That way, the index of refraction could be fixed inside the cylinder. More advanced versions could eventually incorporate metamaterials that are flexible and can twist and still make light flow within the metamaterials on the correct path. In this way, anyone inside the cloak would have some flexibility of movement. Some have pointed out a flaw in the invisibility shield. Anyone inside would not be able to look outside without becoming visible. Imagine Harry Potter being totally invisible except for his eyes, which appear to be floating in midair. Any eye holes on the invisibility cloak would be clearly visible from the outside. If Harry Potter were totally invisible, then he would be sitting blindly beneath his invisibility cloak. One possible solution to this problem might be to insert 2 tiny glass plates near the location of the eye holes. These glass plates would act as beam splitters, splitting off a tiny portion of the light hitting the plates and then sending the light into the eyes. So most of the light hitting the cloak would flow around it, rendering the person invisible, but a tiny amount of light would be diverted into the eyes. As daunting as these difficulties are, scientists and engineers are optimistic that an invisibility shield of some sort can be built in the coming decades. Invisibility and nanotechnology. As I mentioned earlier, the key to invisibility may be nanotechnology, that is, the ability to manipulate atomic-sized structures about 1/1000th of a meter across. The birth of nanotechnology dates back to a famous 1959 lecture given by Nobel laureate Richard